Hi everyone and welcome to Desart's channel. It's time to make some experiments with hello10. But before the practical part, it's nice to make some simulations. I'm going to do them with helloApp from the Matlab Simulink, and Desart provides me some theoretical information. It says how to make the simulations and also some theoretical part behind the control systems theory, like how important is Laplace function and how important is the block diagram. Well, I've read all the theory and feel ready to start. Experiment 1!
Okay, so let's start our, simulations. We choose English here in helloApp, and then some pre-lab section we might open. Please don't change settings or COM ports since we don't connect the hello10, we don't need them. Let's open pre-labs, and according to our guideline we open pre-lab 2 model 1 to simulate the PID controllers, and we are waiting for our model to open. In our first experiment we are planning to check in real life how PID controllers influence our errors. We have two types of errors here, fixed error and growing error, and three types of different controllers. So first let's check the value of fixed error, and it's 2. At the same time I put a value of 5 to P controller and make other controllers 0. Let's check what's going to happen. I run my program and then I open the scope, and I see that my error, which previously was only 2, now it became 10 because P is something like proportional controller, so just our fixed error multiplied by proportional controller, and we got 10 at the end. Now let's check the influence of I controller, and consequently I made it 5 and other controllers I make 0. And again I run my program, I open my scope, and what can we see? Something like a ramp function which is constantly increasing because I is integrating controller. Well, now you can pause this video and just try to predict what will happen if we only leave the D controller. I'm also giving the value of 5 to it, and other controllers are 0, and we start our program. And it is 0. Right, that's what you expected, right? Because the D controller, it differentiates the function, and since we had the fixed error of 2 value, and you know the derivative of a constant is simply 0. Now it's time to simulate the growing error with PID controllers, and let's start with P controller again. But first let me check the value of growing error. It has a slope 1 and it's simply a ramp function. Let's run our program. And now let's check what happened. We again have the ramp function, but now it's multiplied by 5. That's what we expect from the P controller. Let's make it 0 again, and let's integrate this time our error and check what happens. Well, something like parabolic function. Well, what do you expect from D controller if I give the value of 5 and if I give the value of I to 0? Well, I predict that it's going to be not a ramp function anymore, but something like a unit step. And it's exactly like this. It's a unit step function with the value of 5. Simply we just take the derivative of ramp, and that's it. Well, okay, that's a PID controller simulations. This simulation showed us the influence of P, I and D controllers on the different types of errors. I hope it was quite understandable, and now it's time to make a second experiment. Before we start our second simulation, I would like you to have a look at this graph, which is provided by Desart in their theoretical pages. And the graph of unit step response looks like this. It has a rise time, it has also a settling time, and you can see the rise time is over here, settling time is there. It has an overshoot, like the highest peak in our function, You can calculate all these things by using some specific mathematical formulas, but we are not going to do this right here. And the last part of this graph is steady state error, which occurs after some time when our signal becomes like more or less like behaves in the same way over the period of time. And now let's try to do our second pre-lab simulation. And according to the guideline here, we need to use this transfer function, and you remember transfer function is in a Laplace form. And again, let's open the pre-lab 2, how it says, and start. Wow, such a surprise. I didn't expect that this model is empty, so now to simulate it, I need to create my own model according to the desired. Let's try to do it. First, let's start with transfer function. Maybe we can write like transfer function with, okay. And put here unit step function, or just maybe step, and connect it like this. And we need output here, and maybe we need some feedback. Maybe connect it to scope. Well, and I don't know what I've created a moment ago. I just made some open loop function. I was a little bit disappointed that my model isn't that good, but this simulation was a good surprise and it worked. You can see my scope results, and the graph is exactly like we saw. Like we have some rising time here, and I put the initial input of my transfer function to 0.5, like it was my craziness. Then we have an overshoot, and somehow we come to the steady state error. Let me fix my transfer function. Let me not put the initial input and initial output values, and run the program one more time. Yeah, and you can see we start from 0, we have some rising time, and then it settles and it works, I believe. Well, yeah, the simulation works, the graph is the same.
Thank you for watching this video. All experiments are finished and done. I hope you like it, and I hope I could explain to you how to use helloApp, and we did all the simulations. So see you at the next video when we are trying to really use the hello box.